So as you're taking a look at this problem, I hope that your brain automatically went to thinking about this equation. A of t equals p times 1 plus r to the t. Some of you already have this memorized. Some of you are getting close to have it memorized. Really, at this point, we've used it enough where I hope you do have it memorized. And if you don't, realize that now's the time to get there. So continue working on it, continue seeing why. Now, how do I know to use this particular equation? Because we're increasing by a certain percent each year. Anytime you are repeatedly increasing or decreasing by a certain percent, this is your equation. That's your winner right there. All right, now let's go ahead and plug in the stuff. Remember, P stands for principal. That's my starting value. R, that's my rate. That comes from my percent. Remember, turn it into a decimal. So I do the 10 divided by 100. And then T, that's my number of years. Now in this case, I'm getting the stock when I turn 18, and I want to leave it there till I'm 60. Again, notice the whole idea here. We invest the money, and then we just let it sit there. I'm not worried about what it's doing tomorrow. I'm not worried about what it's doing in a week. I'm worried about what's it going to be when I'm 60. So overall, big trends is what I'm interested in. When I plug that into the equation, this is what we're looking at. We're leaving the money there for 42 years. Now when we go and do that calculation, remember, do the stuff inside the parentheses first, and then we go ahead and raise it to the power of whatever it is. So I do the 1 plus 0.1 on my calculator, I get 1.1. I then do that number to the power of 42, and I then take that number and multiply it by 1,500, and we get $82,145.55. A very tidy return on our investment. Yes? Now, having done that, I want to ask a couple follow-up questions. What if we had taken the exact same $1,500, but we decided we don't have a lot of money right now when we're 18, so I'm going to wait a little while because, it's too hard to put that money aside right now. So I'm going to wait till I'm 28 and invest it then. How's that going to change my number? Do that calculation. All right, so in order to do this one, of course, everything in our equation is the same except for the number of years. In this case, it's going to be 32 years. So we do the 1 plus 0.1. So we got 1.1. We do that to the power of 32 now, and then multiply it by the 1,500. In this case, we get $31,670.67. Do you see the value of starting early? Because that's one of the questions that often comes up. Does it really matter if I start that early? Because I don't have as much money now as I will have later. So I'm trying to save every penny I can for this and for that. But notice what a difference it makes down the road. And the thing is though, when you're 18, you have a starter job generally. You're making probably minimum wage or something close to it. And so a lot of people think, well, I'm hardly making anything and I'm not getting any hours because I'm going to school, so I don't have any money for it. I'll do it later. So then they think, okay, I'll do it when I'm 28. But when you're 28, many of you are still going to be at the start of your career. If you chose to go to college and go that route, at age 28, you'll be fresh out of college, start your new career. So you won't be making as much then either. Or if you're not going the college route, you probably at age 28 have a young family. And you're actually having kids, and kids are expensive, right? And so you're thinking, okay, at age 28, I don't really have much money to be investing there. I'll go ahead, I'll do it soon, I promise. And then age 38 comes around, and you still haven't started. But at least now we finally got enough money flowing around where we can go ahead and do that. So at age 38, what will that number be? And so in this case, if we start at 38 and are hoping to retire at 60, our investment grew to be worth a bit over $12,000. It's $12,210.41. That's still better than nothing, right? We still put $1,500 in and got out $12,000. It's a good gain. But compare that to what it could have been. If you just take the time now and force yourself to take some money and put it aside, it's going to pay off hugely. Notice what happened up here to these numbers when we waited to start investing. At age 18, it becomes $82,000. At age 38, it becomes $12,000. It's a huge difference. This is why whenever you're off like doing that research on your own, seeing, okay, what do people say about investing in general and stuff like that, a lot of you discovered that one of the first things that came up a lot was start early. This is why. Compounding interest is extremely useful for you, but you have to give it time to do its work. All right, so we're going to shift gears from the compounding interest equations to graphing exponential equations. Notice the unifying theme of all of them is exponential. All of these have our x's and the exponents. And so we looked at the equations. Now we're going to be looking at the graph. So take a moment, write this equation above your first graphing grid, and then go ahead and make the graph of this, and then we'll come together and make sure that you're remembering that process and everything involved with that graph. All right, so when doing this, you notice I put these questions down the left-hand side to start with: parent function, transformations, asymptote. Some of you will choose to actually write that stuff out, but you don't have to. But you do need to at least be thinking about it. You need to kind of know that stuff as you're looking at one of these equations, because they tell us so much about it. Like parent function. The parent function is just telling us what's the basic function that my graph is going to be based off of. That's always the one without any transformations in it. So that's just the 2 to the x. The transformations are, what am I doing to that original graph? Well, in this case, you can see that's the -7. Now, the -7 is hanging on the end. So that means it's going to be moving my graph, or shifting it, down 7. Now, since I'm shifting this graph down 7, that changes the asymptote. Remember, that's that fancy mathematical word. Basically, that just means the line that the graph will approach, but never actually touch. And so, since I graph 2 to the power of x, and that would give me an asymptote at 0, when I graph it with the -7 in there, it means that my asymptote is going to be down at -7. And so the asymptote is at y equals -7, and when I go to make my graph, that's the first thing I put on my graph. I draw in a dotted line, horizontal, down at -7. Yes, it needs to be dotted. Oftentimes we get a little bit sloppy, we want to go fast, and we make it solid. But then that means something different mathematically. It means you're making 2 graphs, and one of them isn't actually the graph here. The dotted line says, this is here just as a guide. And that's what you want to be putting in. All right. From here, to make our graph, we always start up 1. Now, when I say up 1, I actually mean at the y-axis. So your very first point is going to be 1 above your asymptote on the y-axis. You can put a little square around there so we can track which was that first point as we go. So the first point is 1 above the asymptote. From there, as I head to the right, this is 2 to the power of x. 2 to the power of x means I'm going to be multiplying every height by 2. So right now, I started up 1. Next up, I would then go 2. I would then multiply that by 2 to get 4. I'd then multiply that by 2 to get 8. I'd multiply that by 2 to get 16, and so on, and so on. What that means graphically, I started by going up 1. Now I'm going to count up 2. And I'm going to put a dot there. And then I'm going to count up 4. And I'm going to put a dot there. And then I'm going to count up 8. And notice I'm saying count up 8. I'm counting up from the asymptote every single time. Will this 16 fit? Can I go up 16 for my asymptote in this case? Yes, there actually is enough room to actually plot a dot there, so we need to do that. When you plot all of those, these are the locations. Make sure each of those points is in the right spot. Now as I went to the right, every point was twice as high. Okay, so then what happens as I go to the left? Well, what would be the opposite of multiplying by 2?
Dividing.
Yep, dividing. We're going to divide by 2. So where I start with 1, the next one's going to be half as tall as that. So like at a half. The next one after that is a half as tall as that. It's getting very small very fast, right? So that's going to be at like a quarter. I mean, this is where you kind of wish that on your paper you could do one of these, right? I can't tell where it goes. I'll just zoom in. Well, that would be nice, but we can't on our papers, right? So you just get as careful as you can, be as accurate as you can, but realize you're going to be close, but not necessarily perfect. Just plot 2 or 3 points on that side, and it'll give you a good idea about exactly where that goes. Now, once you have at least 2 points on each side of your first point, you got enough points. You can go ahead and see where the curve is. Go ahead and draw the curve in through those. And then you have your graph. You're done. That's what we were looking for. Notice this one's moved left 4. How do I know it's left? Because the plus 4 is up in the exponent. It's up with the x. So that's how I know it's going left, not up or down. Now, if it's not going up or down, your asymptote's still going to be at 0. Now, for asymptotes at 0, start by drawing that in. That way you can see everything's relative to the dotted line. Because I don't care about where the axis is. I care about where the asymptote is. And of course, remember that your first point is one above that. But for some of you, this is actually a tricky piece. So that's why I'm wanting to spend some time with this one. Normally, that first point is up 1 on the y-axis, right? But it's not going to be here. Not because we're changing the whole up 1 thing, but because it's shifting to the left 4. So I need to take that point and I need to move it 4 units to the left. So that means this is going to be your first point right here. All right, once we plotted our first point, no matter where it ended up, once we have that first point, the pattern is always the same. And this is what is great about math. You don't have to memorize 10,000 different graphs, you just have to memorize a few methods. And in this case, whenever it's 2 to the x, what it's telling us is double my height as I go to the right. So, up 1 becomes up 2. Up 2 becomes up 4, because I'm doubling it. Up 4 becomes up 8, because I'm doubling that last one. And so I plot each of those points, doubling my height along the way. If I kept going, after going up 8 there, I'd be having to go up 16. And then I'd have to go up 32 and 64, basically just doubling every single time. All right, now if I'm doubling on the right, that means, of course, I am cutting it in half going to the left. And again, just be as precise as you can. Doesn't have to be absolutely perfect, but it should be pretty good. And then once you have those points plotted, you can draw your curve through it. So we've done the individual transformations. Now I want you to put them together. Please graph this equation. And in this one, I didn't start by writing down the side there, those things that we should be thinking about. Hopefully you already had your brain kind of already wondering about these things. Parent function, transformations, asymptote, all that kind of stuff. This is what those would have been, what you would have had in mind as you start making the graph. The parent function is 2 to the x, so I know it's going to be something with this general shape, where it's doubling as it goes along. The transformations, though, tell us where that graph is getting moved to. It's going to be going left 4 and down 7. Now, since it's down 7, that means my asymptote is at -7. When I go to make the graph, that's the very first thing I draw in is the dotted line down at -7. This is the time when we really start seeing the need to draw that in too, because otherwise targeting gets to be a problem. I'll often see people in math who want to take shortcuts. And one of the shortcuts people try to make on this one is they try to not draw in the asymptote. And what ends up happening is that they normally will go down and they'll put their first point right here. Because in their brain, they have down 7, which is correct, but of course that's where the asymptote is, not where the first point is. The first point, of course, is always one above the asymptote. By drawing it in, you can correctly target it. It also helps you counting from there, because of course, all of our heights for our other points are all relative to that asymptote. They aren't relative to the x-axis. I don't care where the x-axis is. All I care about is counting from that asymptote. And so I'm up 1. As I go to the right, I'm going to double that height all the way along. So there are where each of your points should be located. Make sure each of those got plotted in the right locations. All your counts are right. Got those by doubling. As I go to the left, of course, I'm cutting them in half. And then once I've got all those points plotted, I draw my curve through. It's a nice smooth curve, and you're done.